I am delighted to give the stage to Chad Nestor, who will be talking to us about the free cornering of a monoidal category. So please, Chad.
Thanks, Tim, and thanks, Bryce, for inviting me to speak at this. And my name is Chad. I'm a PhD student at Tallinn University of Technology, studying with Pavel Sobocinski. And what I wanted to talk to you about today is a construction that I've been interested in for the past couple of years. It's quite simple. I'm not sure we'll need the whole hour, but I'll try to go over all the results I have about it, and you feel free to interrupt me and ask questions and so on. Let's keep it relatively casual. So the construction is called, it's the free cornering of a monoidal category, and it's going to be a double category, which is what's related to this workshop. And the setting is going to be quite a bit simpler than the setting in, I imagine, most of the talks at this workshop, because the double categories we're going to talk about are strict, in the sense that there's no weak direction. Both directions will be, strict. And further, the double categories we'll work with will have one object most of the time. Yeah, I think in this talk all the time. So the set of objects of our double category is singleton, which makes things a lot simpler. So for example, instead of horizontal and vertical categories, our single object double categories will have horizontal and vertical monoids, because that's what a category over one object is. And we're going to be using these sort of string diagrams for double categories a lot. So instead of drawing the cells of a double category, like in the sort of normal way you see here on the right, instead we're going to draw them this way. You see here on the left, we're going to take the Poincare dual of that diagram to represent the cells of our double category. Where here, well, so A and B would be drawn from the horizontal monoid, of course, just like over here, these would be from the horizontal category. And X and Y would be drawn from the vertical monoid, similarly. Thanks. Yep. And so these, it's kind of natural to write down composite cells using these string diagrams, where a vertical composition is, again, you just put them on top of each other and connect any wires. And you can only do that when the boundaries match. The vertical identity is just a vertical wire. And the same for horizontal composition, where the equations of a double category sort of mean that many of these diagrams are unambiguously interpretable. So for example, the interchange equation relating horizontal and vertical composition means that there's only one way to read this. It doesn't matter how I built it up, I get the same thing. A little bit more about single object double categories. In particular, each single object double category induces two monoidal categories. These will also be strict monoidal categories, like our double categories were strict double categories. So we take our double category and we'll say that a cell of it is vertical if its horizontal boundaries are trivial. I think we should call those the vertical boundaries. But so it's vertical if the things on the left and right are both the unit of that monoid, which we'll sort of represent by not having a wire there to say, no, there's really nothing there. And if I consider the vertical cells of any single object double category, well, then they form a monoidal category, which we'll call sort of V of D if we want to use notation, where composition in the monoidal category of vertical cells is horizontal composition of cells, vertical composition of cells in the double category, put them on top of each other, and the tensor product is given by horizontal composition. And then I can do the same thing for what we will call horizontal cells, so the ones with trivial top and bottom boundary, and they also form a monoidal category. So a single object double category is like two monoidal categories glued together. And so now we're going to start building up to this free cornering of a monoidal category construction. The first thing we need to talk about is the monoid of exchanges. That's what I'm going to call it. So we'll start off, we'll say that A is our monoidal category. And we want this sort of A circle bullet, I'll move the mouse here. This is going to be sort of the free monoid on polarized objects of A. So polarized objects of A, the sort of set here without the star, an element of it will be an object of A together with a polarity. And we'll write it sort of above and to the right of it as a superscript like this. And then a sequence of those, that's an element of the free monoid over that set. We'll write sequence concatenation with the tensor product, just because that's going to work out nicely later. And we'll write I for the unit of this monoid. And, I called this the monoid of A-valued exchanges. And the reason for that is that we're going to interpret these polarized sequences of objects as exchanges sort of with a left participant and a right participant. So here, say Alice and Bob, where if A, B, and C are objects of A, then I have an exchange, an element of this monoid, A circle, tensor B bullet, tensor C bullet, say. And the way that I understand that as an exchange with a left participant and a right participant is that, well, the left participant, Alice, has to give Bob an instance of A, and then Bob has to give Alice an instance of B, and then Bob has to give Alice an instance of C. And so that sort of describes this exchange protocol that a left and right participant must do. And now we come to the central construction, again, over some monoidal category A. And it's going to be a freely generated double category, that is free cornering of A. And so we have to give you I have to give you the horizontal category, the vertical category, and the cells, and then we're going to quotient them by some equations. And then, you know, the free double category over these is kind of the obvious thing, where you get all of the cells in it that you could get by composing your generating cells modulo your equations. So the horizontal monoid, the things that will go on the top and bottom boundary of our cells, is the object monoid of our monoidal category A. And the vertical monoid is going to be this monoid of exchanges that we just introduced. And the generating cells, there are going to be two sorts of them. And the first sort is that for every arrow, say f from A to B of our monoidal category, we'll ask for a generating cell sort of representing f with trivial left and right boundary, draw them here, and top boundary A and bottom boundary B. So we are sort of asking for a copy of our monoidal category A going from top to bottom, if you like. Subject to some equation saying that if I sort of include two things and vertically compose them, that should be the inclusion of the composite, and so on for the tensor product and identities to make this coherent. And then the second sort of cell we'll ask for is corner cells to generate our double category, where for every object of A, we'll ask for these 4 corner cells of type A. Sorry. And to sort of make this coherent with our interpretation of the vertical monoid, the monoid of A-valued exchanges, and our thinking of these F morphisms as going from top to bottom, well, these are sort of going to be things that get and put, or sort of receive and send, in some sense, things along the left and right boundary to participate in these exchanges. So this one would get an A along the left boundary, have it at the end. This one would start with an A and send it out along the right boundary. And these are the dual of this. So I could get an A from the right and have it at the end, or I could start with one and send it out along the left. And we'll ask that we'll quotient the resulting thing by the Yankee equations that says that sort of if I get something and then send it out, this is, I'm not sure how to say this in words, but we need these equations to make this coherent. And another reason we would want these equations is because this is a very common structure in the theory of double categories, right? This is the structure of a pro-arrow equipment, or companion and conjoint structure, or all sorts of other things. But I might call it corner structure because of the string diagrams. I'm not sure. And so I think that this free cornering construction is very interesting. And the reason I think it's interesting is because if we interpret the arrows of the monoidal category A that we started with as processes, or if you like, resource sort of transformations, where I start with the things in the domain and I end up with the things in the codomain as a sort of process to get one from the other, then I can think of cells of the free cornering of that monoidal category as processes that interact with their environment via these simple A-valued exchanges. So for example, if I had a morphism of the monoidal category A called need, and that in this case would have domain do, which would have to be an object, and codomain do, so that would be like I could take some dough and transform it into more dough by kneading it, or a different dough. And say I had another morphism bake that would take dough and an oven, represented by sort of dough tensor oven as an object, and I could bake it into bread and also the oven, because I would still have it. Then I could form these two things in the free cornering. These would both be cells of the free cornering, where now this process would sort of, start with some dough, knead it, and then send the result out along the right boundary of the cell. And then this process here on the right would receive some dough on the left boundary of the cell, starting out with an oven, bake that dough in the oven, ending up with bread in an oven. And then if I compose two of these processes, these cells horizontally, using my horizontal cell composition in my double category, then that's like them interacting with each other, where the yanking equation says that it sort of didn't matter that it was originally two separate things, if that makes sense. So if I composed these two horizontally, then I would get this cell, and I could sort of use the yanking equation to get just a morphism of my original monoidal category. So I can describe parts of these processes and decompose them. That's the basic idea. That's the cool thing, and the rest of it is all analysis, I guess. So this free cornering of a monoidal category turns out to have a lot of structure, or at least some structure. And the first bit of structure I want to introduce, possibly the most important bit, is what I want to call crossing cells. So where crossing cells will be these things like this, where it's just one wire crossing the other wire. And so this is an inductive definition of a crossing cell for every, so, you know, I want a wire B to cross some wire of any type going from left to right. So that's going to be any element of my monoid of exchanges. And so we'll define this inductively. If I have the unit of my monoid of exchanges, well, then the crossing cell is just going to be the vertical identity on B. And we had to be symmetric for this to work. And if I have just sort of a sequence of length 1 in my monoid of exchanges, then if it's sort of circle polarized, which in our interpretation is sort of a thing going from left to right, and I want to cross that with B, well, then the way I'm going to define the crossing cell is by sort of using the corners to make things all go vertically, use the braiding map for my symmetric monoidal category to cross them over each other, and then use the corners again to make it go in the right direction, and vice versa, or sort of dually for the other case. And then in the inductive case, if I want to cross lots of wires over each other, I can do it sort of for the individual wires. I hope that makes sense, right? And these kind of look like they should be interesting, and they are interesting. What we can do when we have these crossing cells, a consequence of having a braiding map, having a symmetric monoidal category, is that we can define the tensor product of cells in the free cornering of A. And we do it like this. We sort of take alpha and beta, we put alpha in the top left, beta in the bottom right, and cross all the wires over each other. And this tensor product of cells makes the free cornering of A into what's called a monoidal double category. So this is a notion due to Mike Schulman, I think. And a monoidal double category is so a pseudo-monoid in the 2 category of double categories, strict double categories, strict double functors, and vertical transformations. Yeah, so that's cool. We have a monoidal double category. And the crossing cells are also quite helpful if you want to draw more complicated diagrams. Just you sort of read them like you would read the braiding in a monoidal category in one of these sort of process theoretic interpretations, where here I would have in this same sort of bake knead, and here we have mix that mixes flour and water into dough. Then I could form these processes where here I sort of get dough along the right-hand side, and I start with an oven, and then I use my oven to bake the dough into bread, and I send the bread out along the right-hand side again. This one in the middle would compose with that. It just starts with flour, sends it out along the right, gets dough along the right, sends it out along the left, and gets bread along the left, and ends with it. And then this one here starts with water, and its sort of job is to mix flour into dough, getting it along the left and sending it out of the left. And then when I compose all of these horizontally, because of course these are all horizontally composable, again, I get sort of a morphism in the original monoidal category describing what has happened. The rest of the talk is going to be about a couple of different other things that we can do with this free cornering. But I want to, this is the big idea, that we can sort of decompose these processes. And we see the arrows of the monoidal category as processes by working in this free double category, the free cornering of that category. These string diagrams I've been drawing, there's been a little bit of work on them specifically for pro equipments. In particular, David.
I think we've lost Chad. Is that just for me, Bryce?
No, I've also not, he's frozen.
Okay, let's give him a second and see if he comes back. Okay, he's left. You're back, Chad. Sorry, let me, you can unmute yourself.
Sorry about that. I had a connection issue, I think.
It's okay. That's the joy of an online conference. So
yes. All right. Right. So these diagrams are sound in the sense that if
your screen has stopped sharing though.
Okay.
Sorry.
That's fine. I might have to rejoin with the other one too, because I've lost the screen sharing.
If you
Oh, no, there
like,
it is.
I can share your slides for you and you can tell me when to advance, or you can, oh, no,
It should be okay now,
Perfect.
right? Yeah, there we go.
Brilliant. Thank you.
It should be full screen and we should move that little thing. Okay. Right. So a cool thing about these string diagrams we've been drawing for pro-aero equipments is that they're sound in the sense that if two of them are connected the same, then they represent equal cells of the category, the double category. So, you know, I can do this kind of reasoning where I have something that might look kind of complicated and I can say, well, you know, that's this sort of thing. And then I can pull those wires tight. And that's a valid principle of reasoning when I'm using these. And as a consequence of this, if we consider the vertical cells of the free cornering of some monoidal category A, so the ones with trivial left and right boundary, well, sort of then immediately we know that that monoidal category is exactly the same as the one that we started with. So the vertical cells are just the monoidal category we started with, which makes sense. The horizontal cells, so the ones with trivial top and bottom boundary, are less well behaved or more interesting than the vertical cells. This is something to study. So for example, in the horizontal cells, what are arrows in the category of horizontal cells? Well, they're between exchanges. And in particular, there are isomorphisms between all of the exchanges that sort of should be the same. So for example, you know, using our reading of these elements of this A circle bullet monoid of A valued exchanges, then A circle tensor B circle, well, that's the exchange in which the left participant, who we'll keep calling Alice, has to send Bob, the right participant, an A and then a B. And that's kind of morally the same thing as Alice sending a B and then Alice sending an A. It doesn't really matter which order we do that in. And indeed, these objects are isomorphic in the category of horizontal cells via, you know, this and this are the two halves of isomorphism. And similarly, we have the dual version where A bullet tensor B bullet is isomorphic to B bullet tensor A bullet in the category of horizontal cells. So similarly, we have the exchange where Alice sends an A and then Alice sends a B. Well, that's the same as the exchange where Alice sends an A and a B, and the dual version. And the exchange where Alice sends nothing is the same as the empty exchange where nobody does anything, and so on. This category H of A does not have to be symmetric monoidal. In fact, it's usually not. And sort of intuitively, the reason it's not is that, well, we have an arrow from A circle tensor B bullet to B bullet tensor A circle, pictured here. All of these are sort of equal forms of it. There doesn't have to be any arrow going the other way, much less an inverse to this arrow. If you stare at it for a bit and you try to construct one, the reason that there's no candidate inverse to this arrow in general is that our sort of interpretation is a good one. And having a candidate inverse to this arrow would involve giving things away that I don't have yet along one of the boundaries. So this is kind of neat. Maybe this is some sort of important causal structure, or maybe it's just a coincidence. Other properties of the horizontal cells, so these are kind of obvious, but we'll go over them. One way you can think of the horizontal cells, at least conjecturally, is that it's the same as freely adding a formal dual in the sense of compact closed or autonomous categories to every object of the monoidal category you started with. But that doesn't really help us understand what it is as a monoidal category. So we'll go over some of the properties. So sort of unsurprisingly, I get a copy of A and A up in the horizontal cells of A, where I use the white sort of corner structure, the left to right one to embed it, and I get a copy of A, and I can also embed it sort of going backwards using the black corner structure to get a copy of the dual of A. And then, as I mentioned a moment ago, every sort of right, A circle is sort of always formally left adjoint to A bullet in the horizontal cells. And this is that perspective where we're formally adding a dual to every object of A. Here, A circle would be the representing the object of A, just by these shapes that I can make here. And that, you know, if you've seen the string diagrams for compact closed categories, that makes perfect sense. If the monoidal category we start out with is spatial, so spatial meaning that you know, I can always move things across wires like this. So for example, every symmetric monoidal category is spatial. Then the horizontal cells are also spatial by this argument here. But they don't seem, whoops, right. Yeah, they don't seem to inherit any other structure of A in general. And we'll talk about that more in a bit. Other interesting structure on the category of horizontal cells is that there's an involution. So I can define this involutive operation on the cells of A, where I sort of take the mirror image of all of the corners, take the mirror image pointwise of vertical composites and flip horizontal composites, introducing a swap here to keep things sensible. And when I restrict this to the horizontal cells, this gives me a contravariant involution on that category. And also it preserves the tensor product, which is weird. You know, people work with monoidal involutions, but monoidal involutions are, involutions on monoidal categories that flip the tensor product. So I would have that F tensor G star is G star tensor F star here. But so this isn't a monoidal involution. This is something else. So that seems to be an important piece of structure as well. That's kind of all I know about it. In general, the horizontal cells, they don't seem to inherit any of the structure that A has sort of as a monoidal category. Except that if A is compact closed, then A is equivalent to the horizontal cells of the free cornering for reasons of general abstract nonsense. And it's weird. The horizontal cells are a good counterexample for a lot of things like this. Show me a monoidal category that's not symmetric or not this or not that. In the next part of the talk, I want to talk about something that you can do with the horizontal cells, and this pertains to what are called optics. I don't know a lot about optics beyond this stuff, but I don't know what to tell you, so I'm not sure how to motivate this. Bryce knows a lot about optics. So I'm going to tell you what one is, and it's not going to make a lot of sense. And then I'm going to tell you what one is again in the language of the free cornering that we've been developing so far, and then hopefully it will make a little bit more sense. And so if you know what optics are already, this might be pretty cool. And if you don't know what optics are already, this might be a way to understand what optics are that is easier than reading the literature. Yeah, so sort of elementary, an elementary presentation of optics is that an optic in a monoidal category A of type AB to CD, where A, B, C, and D are objects of the monoidal category A, is a pair of arrows of A, alpha and beta. The M here is not important, where, although it does tell us what type alpha and beta have to be, where sort of you imagine this diagram here, alpha is from A to M tensor C, the M wire is the one that goes here, and beta is from M tensor D to B. And if you've ever encountered these, it's probably in the context of lenses, where lenses are sort of an important kind of bidirectional transformation, and lenses in a Cartesian monoidal category, sorry, optics in a Cartesian monoidal category are what people call lenses. So, and we have to quotient these pairs to get sort of true lenses, to get a category of them. We have to quotient these pairs of morphisms by these sliding equations, where intuitively in our sort of intuition for lenses diagram, it tells me that if I had something only on this wire that crosses the components in the first component, but I could also have it in the second component, and that should sort of be the same thing. And optics form a category where we're not going to read out the definition of that, but intuitively we put these diagrams I'm kind of using for intuition next to each other, and that's composition in it, and identities are the one where they don't interact at all, and that's a category. It's the identity on the top, the identity on the bottom, and the wire in the middle is of unit type. The reason I'm talking about this is that the category of optics in a monoidal category A is a full subcategory of the horizontal cells of its free cornering, which is kind of remarkable. So there's this optic diagram about what an optic is in the intuition, and we can take that, and if we try hard enough, we can draw that using the cornering machinery. So here we've sort of got a wire coming in from the left and got a wire going out the right, and below it we've got one coming in from the right and going out the left, and that's kind of got the same shape that this diagram here does. And it turns out that this is this works formally as well. It's not just that they have the same shape, it's that so, the equations work. Here I can slide F between the components of two optics like that. And here, the components of the optics are these sort of alpha and beta cells here. And just because of how free double categories work, I suppose, I can slide the F here like I would in the elementary presentation as well. And it turns out that that's all that I can do. So every every morphism in the category of horizontal cells on objects of the form A circle tensor B bullet. So, this would be A circle tensor B bullet to C circle tensor D bullet, is an optic. The full subcategory on objects of this form is exactly the category of optics, which is maybe interesting because these optics show up a lot in applied category theory. There's this applied category theory conference, and always about a third of it is about optics. So this might be a good way to understand what those are. So for example, something cool that we can do, and in particular do with the string diagrammatic calculus is, we'll prove something about, or we'll state a result about lenses. So lenses, are optics in a Cartesian monoidal category, and every lens can be put into a special form. So this is my lens H, and it can always be put into this form, sort of this get put form. This is enough, giving a sort of get from A to B and a put from A tensor B to A is enough to specify a lens, and every optic always decomposes into this, where this sort of copying thing is the co-multiplication in my Cartesian monoidal category. Yeah. And when we have these get put maps, people talk about the lens laws, where some lenses are good, they behave like we would expect them to do, if the get and put map satisfies certain identities. And I don't think we should spend a lot of time talking about the identities, because I'm not the person to tell you about this. But the remarkable thing is that, the remarkable thing is after another definition, where so this is going to be something that is equivalent to the lens laws, but we'll say that an optic, so a thing H, sort of like this one, in any monoidal category is lawful in case it satisfies these two equations. So there's a comonoid structure on every object A circle tensor A bullet in the horizontal cells, where the co-multiplication is sort of this thing you see here, or equivalently here, and the co-unit is this little thing here, right? And then if an optic A or H, is a comonoid homomorphism with respect to this comonoid structure, then we'll say that it's lawful. And remarkably, if I have a lens and B is inhabited in the sense that there's a formal element of B, then it's lawful if and only if it satisfies the lens laws. And this isn't mine, this is due to Mitchell-Riley, but you can give a nice proof of it using these string diagrams for double categories. So, and so it's kind of remarkable that we can connect these lens laws to this comonoid structure, and the string diagrams make it nice. Related to this work on optics for the Applied Category Theory Conference, various people have been interested in various forms of what they call comb diagrams, where the idea is that a comb diagram is like a higher order string diagram. So if I have my comb diagram lambda here on the left, somewhere an A goes in and the B comes out, and it has these teeth, and the idea is that the teeth are sort of holes in the diagram, and I'm going to put normal string diagrams into the holes to get a normal string diagram out. So in this way, lambda maps string diagrams to string diagrams, so it's kind of like a higher order string diagram. So what I want to be able to do is this thing here on the right, where I could put an appropriately typed F and G in the two holes here of lambda, and the whole thing would just be a string diagram, a morphism in whatever monoidal category. And this is related to the free cornering, because this sort of comb diagram shape, well, that's one way to represent that is as cells of this form in the free cornering of the monoidal category A, where to put F and G in between the teeth here, I connect them using the corners in this way. There's a paper by my colleague Mario Roman called Open Diagrams by Co-end Calculus, where he sort of develops, he formulates comb diagrams in terms of the co-end calculus. And an interesting thing is that formulating them this way in terms of the free cornering coincides with the formulation in terms of the co-end calculus. So this is a way to do these comb diagrams. So more about comb diagrams, you could imagine some other things that you would like to be able to do with comb diagrams that maybe are awkward if you approach it through the co-end calculus, and all the operations that make sense seem to be fairly natural with the string diagrams for the free cornering. So for example, one thing we might want to do is if we had this comb diagram lambda and another comb diagram mu appropriately typed to fit between the first, sort of go into the first gap in lambda, well, then that's something we could do to get another comb diagram. And indeed, of course, we can do that using the string diagrams for the free cornering, as is pictured below the line on the left here. In this way, comb diagrams form a multi-category, which is maybe interesting, right? So the multi-composition is like so. Yeah, I'm sure you can figure that out. And then another thing that we could conceivably do with these comb diagrams is when the teeth sort of match up, I ought to be able to squish two of them together. So I could have the teeth be on the left for one and on the right for the other one. And if they were typed right, I should be able to sort of interleave them, pictured here. And of course, we can do that in the free cornering as well. It all works. I'll mention also the work of James Hefford and Cole Comfort, where they define a polycategory of these comb diagrams. Admittedly, the string diagrams for the free cornering are less good for that, but I don't know if these catch your interest, you could read that too. Oh God. So there's more about optics. We'll try to go, how much time is left? Okay, quite a bit. So I'm saying this because I visited the University of Edinburgh this summer and I talked to Matthew Naglio, who is maybe here, maybe not, I don't know. But, and he tried to explain what a symmetric lens was to me, and I didn't understand it all. So I came back home and I read the original symmetric lenses paper and realized that we could also kind of do a thing like that in the free cornering, using the free cornering of a monoidal category. So symmetric lenses are, they're remedying an asymmetry in the definition of lens or optic in our case. So we had this diagram explaining what an optic was, and you can see that there's an asymmetry. There is a sort of curved wire going down on the right, but there's no curved wire on the left. And surely we should want a curved wire on the left as well. This is the idea of a symmetric lens. This sounds silly, but there is a whole literature on these things, so I think it's worth digging into. So we want to add a wire on the left, and we can do that. And the way that we do it is just we add some things, and we quotient by sliding equations again. So I'm not going to go over the sort of elementary formulation of this, although there will be a paper at some point. And instead of being able to slide the thing only on the right and not having anything on the left, I want a thing on the left and a thing on the right, and I want to be able to slide both of them across the boundary the same way that I could for optics. And we're going to, so there's a sort of elementary definition of symmetric optic here, but the reason it is that way is because we could represent this by defining another category in terms of the free cornering of some monoidal category, the one that we want to talk about symmetric optics in. And it's going to be like the horizontal cells, but things are going to stick out the top and bottom, and we're kind of going to ignore them. So the objects are going to be the objects of the category of horizontal cells, or the collection of objects will be the monoid of A-valued exchanges, the vertical monoid. And arrows, well, arrows from X to Y, there'll be pairs A alpha, and there'll be cells alpha with top and bottom boundary A, so these are all the same letter, and they have to be equal, and left boundary X and right boundary Y. And then we're going to quotient them by all of these sliding equations. So if I have some alpha with top boundary A and B and bottom boundary A, and I had an H from A to B, then the cell sort of B, H composed vertically with alpha, that needs to be the same morphism. That needs to represent the same morphism as the cell alpha composed vertically with H. And they both sort of go from X on the left to Y on the right, say. And the idea is that this wire coming out the top and going out the bottom, that's going to represent our new wire on the left here. And then the sliding equations we've quotiented by are saying that we can slide G across this boundary, where the wire on the right and sliding along the boundary between the two things along the wire on the right, that's already taken care of, like it was for optics. Maybe we can go back. Ooh, it's pretty far. Yes, that can slide anyway, in the same way that it could for sort of normal optics. So we don't have to do anything special for that. Right. So then composition and identities, these will be, so composition is horizontal composition of cells, and identities are, the identity on something is given by the horizontal identity paired with the unit, because there's nothing coming out the top or the bottom. And that defines a category. And actually, it's a monoidal category where the tensor product is given by the tensor product of cells. So great. And now, just like optics were the full subcategory on the horizontal cells of A, on the objects of the form A circle tensor B bullet, symmetric optics are the full subcategory on the objects of the form A circle tensor B bullet of this thing that we just defined. to be, we defined it so that this would happen. And yeah, so this is the sort of decomposed form of a symmetric optic. And I'm not going to go into this here. There's, in the sort of original paper on symmetric lenses, because a symmetric optic is something I'd like to introduce using this, this is what a symmetric optic is. The sort of main result about symmetric lenses that makes them symmetric is that they form a category, and that category is self-dual. And here too, we get that if I have a symmetric optic represented by alpha and beta, then just the category of symmetric optics that we get out this way, the full subcategory on objects of the form A circle tensor B bullet is also self-dual, along with some other things. But this will be out at some point. So we can also do, we get a notion of symmetric optic by doing this construction on the free cornering. Right. So this ends the part of the talk about optics. There are 10 minutes left. Good. Now I'd like to tell you about something completely different that you can do with the free cornering that came up in a different context that I won't talk much about. I'll just talk about the construction. But the context is a paper called Situated Transition Systems that is in the Proceedings of Applied Category Theory 2021, which are now out. And the category sort of interest from our perspective in that work is, so I have my symmetric monoidal category, and I constructed this free cornering, and then I defined this category angle brackets A, where the objects are the objects of A, and the arrows, it's a bit like the vertical version of the one we just did for symmetric optics. The arrows from A to B are cells of the free cornering of A with top boundary A and bottom boundary B. And the left and right boundary are also there, but they're not satisfying any of the required data of a category, they're just there. And then composition is vertical composition of cells, right? And identities, the identity is the vertical identity. So it's a bit like the vertical version of what we just did. And this category is going to be a pre-monoidal category. We'll talk about what that is first. So, in a monoidal category, I can put things next to each other. And in a pre-monoidal category, instead of having one operation that lets me put things next to each other, I have two operations that let me put things next to identity wires. So I have sort of FL times X for every object X and morphism F, which we think of as sort of this string diagram. Yeah. And also I have XR times F, which I think of as this string diagram. So I can put an identity on the right of F, and I can put an identity on the left of F somehow. And on objects, we ask that these two operations are the same operation and that operation is unmonoid. So it's a bit like a monoidal category, but it's not quite as nice on the arrows. And the arrows that are nice in a pre-monoidal category are called central, where what nice means is that they interchange well with everything. So if I put an identity wire on the right of F, and then I put an identity wire on the left of G, and I composed those, well, I would want that to be the same as composing them in the other order, right? I would want to be able to interchange them. And similarly, I would want to be able to do that for all things on the left and right. If I could do that for all G on the left and right, I can interchange them like this, then F is called central. And the central arrows of a premonoidal category are a monoidal category called the center. Why do we care about this? The reason we care about this is that if A is symmetric, then this angle brackets of A category is premonoidal. Actually, it's something called symmetric premonoidal, which just means that the braiding plays well with the premonoidal structure. We're not going to talk about that. But my two operations, my L times and R times operations, are defined like this, where to sort of put an identity wire on the left of a morphism alpha from A to B, well, I sort of put the relevant crossing cell there. And that's my R times operation. And then the other one is I put the relevant crossing cell on the other side. So when I do this, I get a pre-monoidal category, and the center of it is precisely the monoidal category I started with, only the things with nothing sticking out left or right, commute with everything. And if you know what a fried category is, if I start with a Cartesian monoidal category, then the inclusion of that category into angle brackets of that category defines a fried category, which is maybe interesting. So this comes up in programming language semantics, or really more programming language syntax, where you want to be able to talk about morphisms in the Kleisig category of some strong monad, and you can always do that using what's called the arrow syntax. And the arrow syntax works in a fried category. So we could also use the arrow syntax to talk about, say, IO operations as these corners. We could call them get and put on the left and right, say. But there are some barriers to that, and this is very much future work, but I would like to look into representing input and output in programming languages this way. And that's it. I think we're well under time, which is good. I was going to end so by pointing you to my website. If any of this was interesting to you, I'd encourage you to go to my website where you can download all of these papers and more. So there are just some papers written about this free cornering. This one is that one where the angle brackets V shows up. It's sort of, I think it's interesting, but we don't have time. This one was at ACT. This recent one, it has this story about optics, although not the symmetric ones. This is new. This is the journal version of this one. And something exciting is that there's this ACT adjoint school attached to the Applied Category Theory Conference, which is not a summer school, but is kind of like one for young researchers in category theory who are interested in this stuff. And next year, Chris Hernan will be one of the sort of mentors for it. And his project will be about this and also some of his work about pre-sheaf models of monoidal categories, I think. So if you have any students or interested undergraduates who you think might enjoy this, you can maybe tell them to apply for that. Right, that's all. Thank you very much for your time.
Thank you very much, Chad. Some applause. Okay, so people, we have time for questions. People can raise their hands if they would like, ask in the chat and I will read it out, or they can simply unmute themselves and ask directly. And maybe while we wait for the first question, I'll ask a kind of naive one, which is, in the first half of the talk, you said that, like A bullet tensor B bullet is B bullet tensor A bullet. Like this thing is, the order is like this tensor product is symmetric. Like for A bullet, B, yeah, and A circle, B circle. Yeah.
Okay, what's this thing you're going to say, but?
Oh, sorry. So my question was just like, so this comes for free, but like, what if maybe we don't want that? Is there a way to not have that be true? Because I understand you're like, the idea was like, if I'm going to give you something and give you something else, it doesn't matter the order I give it to you in. But maybe sometimes we do care about the order we give stuff in. So can you talk about that?
I think if you care about the difference between Alice gives Bob an A and then Alice gives Bob a B and the reverse, then this is probably not the thing to be working in, because it just does come out of the structure. But I will point out that this category of horizontal cells is not symmetric monoidal in general. In particular, because while I can sort of swap things that are the same color, their order doesn't seem to matter very much. I can't always swap things that are different colors, which again sort of makes sense.
Yeah. Okay. That makes sense. Okay. Brilliant. Thank you. Okay. Does anybody else have any questions? Okay, if not, then maybe we can thank Chad again for the talk.